Hey guys, welcome back to my channel. I'm Karthik Agrawal, who is currently studying in Sri Venkateswara College of Engineering. Welcome to today's video. If you ever wondered how your computer, smartphones, or even server manages all the tasks running behind the scenes, this video will break it down for you. We will dive deep into the structures of operating system, exploring the key components, their architectures, and how they affect performance, security, and flexibility. Today, we will discuss the structure of operating systems. We will explore the various ways operating systems are designed to manage processes, resources, and communicate with hardware. Let's start by understanding the foundation of any operating system. I hope you all are excited for today's video. So, starting today's video, let me ask a basic question. What is an operating system? And at its core, an operating system is the software that acts as an intermediary between the computer hardware and the application of users interacting with the system. It controls all the computer processes, handles memory management, input-output devices, and ensures the safety of the software. The operating system makes it possible for users to interact with the computer hardware in a meaningful way. Now let's understand, why does structure matter? The architecture of an operating system determines how efficiently it can perform tasks, how flexible it is in handling new applications, and how accessible it can be as more users processes are added. Now let's understand at the key components of operating system. Let's start by kernel. The kernel is the brain of operating system. It is responsible for managing the system's resources like CPU, time, memory, and input-output devices. The kernel decides which process gets the CPU and when. It ensures that each process gets the resources it needs. Let's understand system libraries. These are collection of functions that provide common services for adaptation of software. For example, a system library might include functions for read, writing, or file interaction with the operating system itself. Now let's understand the shell. The shell is the interface through which user interacts with the operating system. This could be a CLI, that is command line interface, where user types commands, or a GUI, where that is graphical user interface, where user clicks on the icon to perform tasks. Now let's understand drivers. Drivers are the software components that allow the operating system to communicate with hardware devices. Without drivers, the operating system wouldn't be able to control devices like printers, scanners, or graphic cards. Now let's explore the four main types of operating system. Let's start by monolithic structure. This is one of the oldest operating designs where entire operating system runs as a single large process in one big kernel. It is efficient in terms of performance, but it takes difficult to debug and maintain because of all the components are tightly integrated. Let's move on to layered operating system. In layered operating system, the operating system is divided into layers, each of which handles specific functions. The bottom layer interacts with the hardware, and each layer above it provides more complex services. The structure simplifies the development and debugging, but introduces performance overhead as each layer needs communication with the layer below it. Moving on to a microkernel structure, a microkernel design reduces the kernel to its minimum size, including only the most essential services like process scheduling and memory management. Other services such as device drivers and file systems run in user space, which enhances the security and modularity of the system. However, performance can suffer due to frequent context switches between user and kernel space. Now let's understand the last type of operating system structure, that is modular structure. Modular operating system consists of a core kernel that can dynamically load and unload modules based on needs. The OS remains lightweight but flexible. because the system can add new modules like device drivers or file systems as needed. This provides the benefits of both monolithic and microkernel structures, which helps in high performance and flexibility of the system. Now, let's compare the different types of operating system structures. Again, let's start with monolithic. It is fast because all the operating system services are in one place, but debugging and adding new features can be difficult. Any bug in one part of the kernel might cause the entire system to crash. Moving on to layered operating system. This structure makes the operating system easier to maintain because each layer has a clear responsibility. However, the extra overhead between the layers can slow down communication, especially in systems that require real-time performance. Now, microkernel structures offers enhanced security and stability because services are isolated in separate processes. This reduces the risk of system crashes. However, this frequent context switching and communication between the kernel and user can introduce performance bottlenecks. Moving to the last type of structure, that is modular systems. Modular systems are more flexible and allow dynamic changes without disrupting the entire system. While performance is often better than microkernels, managing the dynamic loading of modules can be complex. Now, let's take a deeper look to the kernel, which is the heart of the operating system. The kernel controls all the system resources, allocating them to various processes based on the priority and needs. Now let's understand the types of kernels. Monolithic kernel. In this structure, the kernel handles all essential operating system functions from memory management to hardware interactions. While this results in high performance, it can be difficult to change or extend because adding new features cause instability. Microkernel. A microkernel is much smaller and focuses on essential services like process management and inter-process communication. Adding services such as file systems, device drivers, and networking are handled in user space. This reduces the complexity of the kernel and improves security, but it can cause performance issue. Let's understand the last type of kernel, that is hybrid kernel. Hybrid kernel aims to combine best of both worlds, blending the performance benefits of monolithic system with the modularity of microkernels. For example, Windows NT kernel is a hybrid providing a flexible and extensible operating system while retaining high performance. Now let's see layered operating system. In layered operating system architecture, the operating system is divided into distinct layers that perform specific tasks. The lowest layer deals with the hardware interactions, while the higher layer handles more abstract services. For example, in OS bar 2 system, one layer may be responsible for memory management while another handles network communications. Advantages: easier to maintain and debug changes to one layer and does not affect others, making it simple to test and implement updates. However, the major downside is the performance overhead introduced by multiple layers for systems that require real-time operations. This can cause delays in processes. Let's see microkernel architecture. The microkernel architecture focuses on minimizing the kernel to include only essential services by moving additional services like device drivers, file management systems, and networking into user space. The system becomes more modular and secure. It is easier to add new services and features because they can run as independent user process. If one service fails, it does not bring down the entire system. However, the performance cost can be high. Frequent context switching between the kernel and the user space can slow down the system, especially if services needs to communicate regularly. Now let's keep a deeper dive into modular OS design. A modular OS design combines the best of both monolithic and microkernel approaches. It can be used as core kernels that can dynamically load and unload modules based on demand. This allows the system to be highly customized and accessible to new hardware or software features. Modularity allows the operating system to be more flexible and extensible. You can add or remove functionalities without rebooting the system, making it scalable and easy to update. While it offers flexibility, managing and testing a modular system can be complex, especially when systems are independent. Now, let's understand examples of operating system based on different architectures. Let's move on to monolithic architecture first. Examples include older versions of Unix or DOS, where performance is prioritized, but flexibility and maintenance can be challenging. Moving now to layered. Systems like OS bar 2 and the system use a layered structure, simplifying the development and debugging processes at the cost of performance. Now, let's see microkernel structures. Minix and QNX are microkernel structures offering modularity and improved security at the cost of performance. Moving for the last, that is modular, Linux and Windows NT are modular operating system that provides flexibility and adding new modules without sacrificing too much performance. Now, to summarize the structure of an operating system, this plays a crucial role in determining the performance, flexibility, and scalability. However, each type of structure, such as monolithic, layered, microkernel, and modular, has its own strengths and weaknesses, and the choice of which one use depends on the specific needs of the goal of the system. That's a wrap for today's video. I hope you have a better understanding on various operating systems structures. Don't forget to like, subscribe, and click on the notification bell to stay updated with the latest video. See you next time. Thank you very much.